All right, everyone. So today we're working on an example of taking our systems of equations and then applying that to an actual application problem that would relate to something that you could see on an everyday basis, or hopefully some sort of context so you can kind of picture how we can apply the mathematics that we're learning in class. So two kids are at summer camp, Katie and Tom, and they're competing in a potato sack race. Katie is younger, so she's given a head start of 30 meters. When the race starts, Katie hops at a rate of 1 meter per second. So a couple of things we should be thinking about right now. She's getting a head start, and we know that she is traveling at a rate of 1 meter per second. So there's our rate. Remember, we're working with linear equations. Tom hops 4 meters per second. There's his rate. So he's at 4 meters per second. Eventually, Tom will overtake Katie. We want to figure out when that would happen. So if we think about kind of interpreting each person's distance being traveled as a linear equation, we know that Katie gets a head start of 30 meters. So she's 30 meters ahead of Tom. So Tom is really starting at 0 at the origin, and we know that Katie is going to be starting at 30. Now, Katie's speed is only 1 meter per second. So I'm going to say 30 plus 1s, because she's going 1 meter per second. S will be for seconds. Now, Tom, he's traveling at 4 meters per second. So that's going to be 4 times S for 4 meters per second. So if we think about these as equations in slope, intercept, remember our variable doesn't matter, but the constant is always your y-intercept, the number by itself. The coefficient in front of the variable is always your rate of change. The order doesn't matter here. I don't need to write this as 1x plus 30 to graph this as a line. 30 is the constant, so we start on the y-axis at 30. Her rate of change is 1 meter per second. Now you'll notice the distance is being measured, each block is 10. Along the bottom, every 2 blocks is 10. So if we are going by 5s along the bottom, in the time, or the distance that would be traveled by Katie in 5 seconds is 5 meters. The distance that would be traveled by Katie in 10 seconds is 10 meters. So if she's starting at 30, she gets to 40 meters after 10 seconds. So it's not just up 1 and over 1 by the boxes. I have to change kind of the pattern that we're taking because it needs to match the units. If the x-axis for seconds is going by 5s and the y-axis is going by 10s, then up 1 and over 1 is really going up 10 and over 5, which is 2 over 1. So I need to make sure that because this is an application problem, what's going on in the scenario of our distance traveled of 1 meter per second, that I'm actually going 10 meters then in 10 seconds. So we go from 30 to 40 in 10 seconds. Another 10 seconds go by at 20, and we would have gone another 10 seconds, or 10 meters. Another 10 seconds go by, and now after 30 seconds, I'm at 60 meters. So our rate of change, sure, it tells us up 1 over 1, but that's only if the units match. Because our y-axis is going by 10s and our x-axis is going by 5s, I need to think about what pace is actually going on here. So here's my graph for Katie. And you're going to see I plotted a bunch of points on there, so that way it's going to be accurate when I sketch my line. Now when I take a look here for Tom, Tom's traveling at a rate of 4 meters per second. There is no constant, so my y-intercept is 0. He's pretty much, think about him starting at the start line. He's 30 meters behind Katie. He's traveling 4 meters per second. So our first block here is at 5 seconds. So in that time period, if we traveled for 5 seconds, basically I'm just plotting these points. How far has he gone after 5 seconds? How far has he gone after 10 seconds? how far has he gone after 20 seconds? And rather than using the rate of change to plot the points, I can just evaluate. After 5 seconds, he's gone 20 meters. 10 seconds, he's gone 40 meters. 20 seconds, he's gone 80 meters. So we can plot the point 5, 20. We can plot the point 10, 40. We can plot the point 20, 80. 20 goes in, 80 comes out. So now I have this graph of Tom here in black. So you can either choose to look at it as a rate of change and count the distance up and over and make sure that it matches, or you can go ahead and evaluate these equations because the equations tell us the exact distance given that number of seconds. I put in 5, I get out a 20. That gives you the ordered pair 520. I put in a 10 for the seconds, I get out 40. I plot the point 1040. I put in a 20 for seconds, I get out an 80. That's the ordered pair 2080. We want to know, eventually Tom will overtake Katie. How far will Tom have to hop? What is this distance here? This distance here is at 40. We want to know how far does Tom have to hop? Tom needs to hop 40 meters to pass Katie. So they start hopping at the same time. When do they pass? Well, this point right here represents where they would be in the exact same spot at the exact same time. So once Tom has traveled this distance of 40 meters, he would then pass Katie, because you will see that his line continues to grow faster and faster and faster in terms of distance because his rate of change is moving that much quicker. I hope this helps with our introduction to graphing systems and applications and provides some context for how you can use this every day.